Assalamualaikum and hi, my name is Nurul Iziana binti Muhammad Nazri. My group and I will present the topic about mission vision for accurate diagnosis of Pekin moles and melanoma in skin cancer. Okay, for the introduction, imagine achieving the accuracy of a precision in disease identification. Computer vision has made this a reality. For instance, in skin cancer, where timely detection is critical, computer vision helps differentiate between cancerous and non-cancerous lesions, ensuring quicker and more accurate diagnosis. Okay, next, let's talk about mole cancer. Computer vision trained with extensive image database has the potential to automate identification processes, reducing human error. This technology could transform the landscape of mole cancer diagnosis. Okay, for this case study, we have chosen to utilize MATLAB Simulink, a versatile platform to implement and simulate various aspects of computer vision application in healthcare. This not only aids in addressing healthcare challenge, but also contribute to the understanding of how technology can improve patient outcome. Okay, next for our objective. Firstly, to conduct a comprehensive analysis of the current use of computer vision in healthcare. Secondly, to explore and apply image processing techniques such as filtering, segmentation, and morphological operation. Lastly, to investigate how computer vision contribute to personalized treatment approach based on individual patient characteristics.
Hi, my name is Natasha binti Khairunizam. My number matrix is 2210620304. The methodology for melanoma detections begins with a comprehensive image acquisitions process where 100 images representing diverse patients' demographics are carefully collected. These images serve as the foundations for creating a representative dataset that aids in distinguishing moles from potential melanoma cases. First, the color images are converted to grayscale, simplifying subsequent analysis by reducing them to a single intensity channel. The introductions of salt and paper noise simulates real-world imperfections, emphasizing the need for the system robustness against noise. Media filtering is then applied to enhance the image quality, effectively removing noise while preserving visual clarity and structure. Media filter is chosen due to its efficiency of removing salt and paper noise. This step is very crucial in medical image analysis as it ensures that the images are of high quality, making it easier to detect potential melanoma traits. Applications of contrast enhancement techniques further improves visual quality, facilitating the identifications of key features associated with melanoma. Trace holding using Orsus method is employed to distinguish between possible melanoma regions and the background, a fundamental step for differentiating melanoma from healthy skin based on color disparities. Subsequently, image segmentation refines the segmented regions, enabling more precise analysis and features extractions. Incorporating morphological filling techniques aids in accurately delineating melanoma lesions borders, closing gaps within the segmented regions and producing a more cohesive and accurate representation of the cell cancer boundaries. This operation is instrumental in improving the quality of medical imaging and increasing the accuracy of melanoma detections. Feature extractions follows where critical attributes of the segmented regions are quantified. These attributes include the area, size of the cancer computed from the segmented region, which provide insight into the extent of the melanoma. Texture analysis utilizing a gray level co-occurrence matrix that stands for GLCM, texture characteristics and entropy based measurement like contrast plays a pivotal role in identifying the textural patterns unique to melanoma. These features are crucial for distinguishing melanoma from moles by recognizing the smallest changes in the texture patterns, aiding the algorithm in making informed decisions. The final step is the process in classifications of the cancer recognitions, leveraging the extracted features including size, the diameter, and the texture. The algorithm distinguishes between moles and melanoma. Specific criteria such as asymmetry, color fluctuations, texture irregularities, and boundary definitions are applied to classify skin cancer accordingly. To sum up, this methodology involves a meticulous image acquisitions process, noise reductions through median filtering, precise image segmentations using thresholding, and feature extractions. These extracted features, along with the melanoma-specific traits, facilitate the algorithm's classifications, allowing for early melanoma identifications and improve patients' outcomes. The systematic approach, which combines quantitative feature analysis and characteristics assessments, enhances the chances of timely interventions and accurate differentiations between moles and melanoma. Here is how we can differentiate between mole and melanoma. Usually, mole will have a diameter less than 0.25 inch, while melanoma will have a diameter greater than 0.25 inch. And also, mole will have an asymmetrical cell, while melanoma will have a symmetry cell. And also, based on the studies, the mole will have a uniform texture and color, while melanoma will have uneven color with different shade.
Hi, I am Nuradira. I will explain the result and discussion. So this is the output of segmented image for mole and melanoma. To get this, by process of performing segmentation from the original image, then convert to grayscale and add salt and pepper. After that, remove the noise by using median filter and apply the contrast to the median filter image. Then use also method. Also apply field operation to get the best binary image. This is the example of feature table from mole and melanoma. This table contains the feature extraction of diameter, size, and contrast from the mole and melanoma image. This is the result for scatter plot. The first one is diameter versus size. As you can see, almost all of the data overlap between mole and melanoma. Melanoma shows larger diameter and size than moles. The data almost all of the data is overlap because the features, diameters, and size will give not a very big difference between each other. So the data we have will give this kind of scatter plot. This is the scatter plot for diameter versus texture contrast. There are some overlap between the two data of melanoma and mole. Melanoma often presents with larger diameter and higher texture contrast compared to mole. So based on the plot, there are clear difference in diameter and texture contrast. This scatter plot for texture contrast versus size. There are many overlap between the texture and size data on the x-axis of the scatter plot. Melanoma tends to have a larger size and high texture contrast than mole. So based on the three scatter plot, we think that diameter versus texture contrast is the best because both of the data from melanoma and mole gives very less overlap data. So it can differentiate both of the image perfectly. The reasons for overlap could include similarities in feature distribution among classes, insufficient discrimination power in the chosen features, or variability with noise within each class. Overlapping scatter plot highlight the needs for a thoughtful feature space and many prompt adjustment in feature selection, extraction, or the exploration of additional feature to improve the overall classification performance.
My name is Nurbatisha Alia binti Shakir. Based on predicted table, the future use are size, diameter, and texture to predict each images. True labels indicates the actual class of test sample image, and predicted label indicates the prediction by minimal distance classifier. For 1, it is indicated as melanoma, while 2 is indicated as mole. Based on the table, we can see that test sample 11 and test sample 18 have the wrong prediction, while the other test sample are the right prediction class. For test sample 11, it is predict as 1, but the true label is 2, while test sample 18, it is predict as 1, but the test sample are 2. The system overall accuracy is 90%. For test sample 11 and 18 have the wrong prediction, while other test sample are true. It may be caused by the classifier may be confused by noise or irrelevant information in the training and testing data, which is why the accuracy may not reach 100%. This noise can come from various sources, such as errors in data collection or variations that are not actually indicative.
Sangat-sangat tinggi. Soalan dia takkan lalu. Awak nak kunci ke sudu? Kan ada cuti. Boleh. Awak nak kunci ke sudu? Sudu emas ke kunci emas? Okey, sudu emas. Nama ibu awak. Okey, kita nak sudu emas. So, we got nak jadi sudu emas. Tapi sudu emas kita bajet betul. Jadi asal ni sudu apa? Sudu besi. Lepas tu, kita nak bagi tak agree or not? Yeah. And so, what happened here? Apa yang terjadi? Mula-mula di sini namanya cannot this one is cannot. Okay. Kemudian kita ada apa? Kita tahu bahawa di cannot atom dari.
Hi, my name is Nur Ilham Izzati binti Zaba. So, in conclusion, the exploration of advanced techniques, including image filtering, segmentation, and morphological operations, added a layer of sophistication to image analysis within medical context, showcasing the potential for refining diagnosis process. The noteworthy success of the minimal distance classifier, attaining a commendable overall accuracy of 90% in differentiating between melanoma and mole skin, serve as a promising testament to the efficiency of computer vision or machine vision, even in the face of challenges posed by data noise and variations. The integration of a graphical user interface serves to enhance the end-user experience, providing an intuitive platform for streamlined image manipulation and analysis. Ultimately, the core motivation underlying this case study centered on bridging the existing gap between technological advancement and healthcare needs, is underscored by the tangible potential of computer vision or machine vision to expedite disease identification, heighten diagnostic precision, and ultimately foster superior patient care through its transformative capabilities. So that's all from me. Thank you.